Sorry for that. Recording is a little chopped off. Okay, so essentially, when you look at the t-score table, you see that this changes because you're trying to kind of estimate the true population variability used on the variability in your sample. So when your variability in the sample is not large enough to reflect the distribution of the variability in your population, you mean to kind of push it a little to make it more closely resembling your population standard deviation. So if you would, if you look at the t-distribution here with increasing numbers, you essentially get here in infinity, you get close at an alpha level of 5%, you get close to that alpha level we utilized with C distribution. So you're getting closer to a normal distribution and the distribution you would expect from the population if the sample size increases. So at 30, you hypothetically could get away, and this is generally accepted by statisticians to get away with C statistics if you have a sample size that is greater than 30. Because with 2.04, you're kind of close to the 1.96, and it doesn't make that much of a difference. Although 1.96 realistically is only achieved with 500. So it's a non-linear increase of the t-score. It basically gets you the significance level of 5%. So this being said, if we go back to our example now, does that answer your question?
Yeah.
Why not the C statistic?
Yeah.
Okay. So we have now a t-score of 0.55. So a c-score of 0.55 does not exceed our critical t-value, and we can confirm our insight that this is non-significant, and our null hypothesis actually is true by calculating 95% confidence interval. And we are doing that by calculating a lower limit and an upper limit. And this is calculated in exactly the same format as we have done it before. So we're taking the mean, we're subtracting 2.31 as the critical t-value that indicates 5% alpha level, multiplied by the standard error of the mean. So this gets us to a lower limit of minus 1.76, whereas an upper limit is calculated as the mean plus 2.31 multiplied by our standard error of the mean, which gets us to 2.87. So now when you look at this in total, so you have your 95% confidence interval, and now think of the definition we had for the STAT statistic, where we compared the mean of our sample and the distribution of the sample means to our population mean. The 95% confidence interval was that interval within which we are 95% confident that we contain our population mean. If our sample and the corresponding confidence interval did not contain our mean, our population mean notably, we would reject the null hypothesis. So now essentially we're doing the same thing, because our null hypothesis now is that we are testing, let me take this calculation now out so we can review it together. So we're calculating now our mean difference of 0.56 against the null hypothesis of 0. And we're dividing it by the standard error of the mean, because that's the distribution of our differences, our mean differences. So now, if the lower limit and the upper limit as an interval do include the 0, they essentially are not to be considered as significantly different from the null hypothesized 0. And Nolan and Einstein have here essentially depiction. So if you have, and now forget about the numbers, we're using different numbers. If you have a mean of 0, that is your null hypothesis. And if around that mean of 0, we are not, actually, this is the better depiction. If our confidence interval does not contain 0, we're having a significantly different result. If our 0 is contained within the 95% confidence interval, we are basically having a null hypothesis that we need to accept. So that's basically confirming our insights from a t-score that is smaller than our critical value. Any questions on that? Was clear? So lastly, with the confident with our hypothesis testing, we also always calculate our effect size, and the effect size is calculated, as we know, as the difference between our difference, our mean difference, minus the null hypothesis, divided by the standard deviation, rather than the standard error of the mean, because the standard error of the mean, we recognize that this is affected by the sample size. That means the standard error of the mean gets smaller with a larger effect size, arithmetically needs to, and the smaller denominator will now increase our t-score artificially. That means we're more likely to see a difference. Whereas the effect size and dividing it by the standard deviation rather than the standard error of the mean will actually result in an effect size that puts more emphasis on the difference rather than the sample size. So our effect size here is 0.18, which we know is, as per Cohen's conventions, to be considered a small effect size. So with 0.2 to 0.5 is a small effect size, 0.5 to 0.8 is a medium size effect size, and everything greater than 0.8 is a large effect size, right? Okay, so freshman 15, what does that mean now for the freshman 15? It means that the freshman 15, based on that sample, is not the same. It's basically, it's not significantly different for college students to go to college, and the weight gain is not significantly different from 0. So these are just random variability that are not systematically different from 0. So there was this example. So Nolan and Heinzen go here to a different example. I'll just quickly walk you through this. So basically, this is slide 9. They're basically presenting a null and research hypothesis, and they're doing the same thing. So basically, it's an example where people recall the details of a news article, and they're comparing the perception of people that there was mental health or mental illness involved in that violent act that was being reported. And immediately after reading the article, people were likely or less likely to perceive this as being associated with mental health and mental illness. Whereas if they tested the same sample again a week after, they were more likely to associate it with mental illness. And the calculation they're doing here is basically data that we have. So this is news report. That's the 4th spreadsheet in the workbook that I uploaded. And it's basically doing the same calculations. So we're calculating again. We're calculating again the differences. Oops. How did I manage that? Okay. So we're calculating again the differences here. We're getting here a difference of 0.2. We're calculating a standard deviation based on our data of 0.141. that essentially is then brought to a standard error of the mean by calculating or dividing this standard deviation by the square root of 5, which is the sample size of 5 shown here in this spreadsheet. And I will post a lecture recording. I did the calculations with the other class before. We're going to do a second example, a different example. So standard error of the mean is 0.063. Then we're basically testing this against a null hypothesis of 0. Since the degrees of freedom are 5 minus 1 equals 4. And we know that if we want a two-tailed hypothesis, we're going to go for the third column. Degree of freedom of 4 corresponds with a critical t-value of 2.78. And these 2.78 are here indicated around a mean of 0. So when calculating the test statistic, you basically get a t-score of 3.17, which essentially leads to rejection of the null hypothesis that there was no difference between reading the newspaper article and making a statement right after reading it and a week later after reading it. So essentially this exceeds that critical value, therefore we're rejecting the null hypothesis. In the calculation of the 95% confidence interval, I can actually show you that spreadsheet. In the calculation of the that is the wrong spreadsheet. So in the calculation of this example, we saw basically a standard error of the mean of 0.14, standard error of the mean of 0.06. And when testing for null hypothesis and alternative hypothesis, we have significantly rejected the null hypothesis, and we calculated the confidence interval, which here, as opposed to the one we calculated, does not include the 0. And this is basically where the confidence interval can be utilized for hypothesis testing, because you're testing against a null hypothesis that there was no change. A null hypothesis of that difference before and after being 0. If 0 is not contained in the 95% confidence interval, you can automatically reject at an alpha level of 5% the null hypothesis of this being significantly different. Because if it doesn't contain it, you're actually less than 5% certain that this should be rejected. So what we see here is a considerably large effect size, which was surprising because the numerical value is small, but the effect size gets you basically an estimate independent of the variability. And for relatively small differences, this mean difference was actually considerably large. So, any questions on the calculations? I think it's considerably simple, right? It follows again the same approach that we have done. The only thing now is that we're calculating first the differences between before and after. We're quantifying this variability of the differences, and we're utilizing the variability of these differences to estimate what the distribution of these mean differences would be if we would draw a repeated sample. And then we're comparing this distribution of the sample mean differences to a hypothesis level of 0, if there's no change. One caveat and one thing that is important for quiz questions, because there's some tricky questions, right? If you, for example, have now a question where you say, is the weight change greater as a value that I would have anticipated? Let's say example being could be the thriving of toddlers, for example, or fetuses that basically have a certain anticipated change, because then your null hypothesis would not be that the mean weight before equals the mean weight after, then the null hypothesis would change to, my null hypothesis actually that the mean weight after minus the mean weight before is greater than a certain anticipated change. So that would basically imply if this would be 0, then I look at no change. If I say this is equals 0.2 or more, for example, then I have an anticipated change. What that arithmetically means then for the calculation of our statistic, that would mean that you're now not subtracting a 0, but you're subtracting here the null hypothesized anticipated change. So if you anticipate a change of 0.2, for example, you would subtract 0.2 from your mean difference. And that would become your null hypothesized value. So it's either 0 if you don't anticipate any difference. And your research question actually says like, okay, was there a change from arriving at college and going back home for the holidays? Or, so then it would be 0 as a null hypothesis. And if I expect a toddler to grow just naturally, because that's what they do, right? Then you basically would use that as your null hypothesized value. So really the key message here is that this change that you're observing minus your null hypothesized value divided by the standard error of the mean gives you an idea what that t-statistic is. And for the rest, it's business as usual. So you basically you get this t-value, you compare this t-value to a critical t-value, but it's an example that you will be facing for the exams. Okay, good. So there are 2 additional aspects to be kept in mind. There is, if you have a within groups design, in a perfect world, you have a randomized study. You have an intervention group and you have a control group. You're comparing the means between those 2 samples using an independent sample t-test that we will do on Wednesday. If you do a within groups design and you're testing whatever intervention you could think of, you may have a so-called order effect. So the order effect essentially means that if I employ my intervention and then study the individual during the intervention period and then after, or I do it the other way around, you have a quote unquote carryover effect of the intervention in the non-intervention period, which means that, if you have an independent variable that essentially determines the evolution and the dynamic of the dependent variable, the order in which that intervention as the independent variable is being administered plays a role. So this is the so-called order effect. So if your intervention has an effect, bless you, and carries over in the non-intervention period, you have an effect of the order in which the intervention is being administered. And that's important because in study design, for example, if you have this kind of design where you study an intervention and then you have a different time period where you don't study the intervention and you have this quote unquote carryover effect, that will affect your insights in that regard because your effect may be diminished or maybe stronger depending on the intervention at hand. Therefore, a lot of studies have something that is called a washout period between the time periods. So they stop all intervention and they basically wash out all effects of the intervention and then study it again. Or what they also do is counterbalancing. So you have intervention 1, intervention 2, and then you have basically with counterbalancing, you would have a difference in who starts with what intervention. So you have intervention 2 first and then intervention 1 after for 50% of individuals, and then intervention 1 and intervention 2 for the other 50%. Thereby, you can kind of minimize this order effect in which an intervention is being administered. In a perfect world, so this design would sometimes, you can even, you can do different scenarios how you administer these orders. Generally, these kind of interventions are called crossover studies, because patients are crossing over from one intervention to another, or from one regimen to another regimen. So it's called a crossover study. If you want to mitigate and minimize the order effect and the associated confounding on the treatment effect, you would also randomize the order. And this is the ultimate form of counterbalancing. So you basically, you balance your subjects to either start with intervention 2 and then cross into intervention 1, or you have the other 50% starting with intervention 1 versus 2, and you randomize them with which intervention they start in the respective group. So in a randomized format, this is called a randomized crossover study. This is counterbalancing. So again, order effect is when the order in which the intervention is administered matters and has effects on the dependent variable, whereas the counterbalancing is an approach, a study design approach to mitigate and minimize the effect of the order effect and the associated confounding. Good. This is only applying in within groups design, and this is quite important. In between groups design, you utilize different approaches to minimize confounding. Good. Any questions on order effects of counterbalancing? If not, then we can do another example. So we have 10 more minutes. No, more. We have 24 more minutes. So let's do another example. So that was conceptually what needed to be discussed. So we have an exam example and we have a mood example. Let's do a mood example. Okay. The following are mood scores for 12 participants before and after watching a funny video clip. Lower values indicate a better mood. So essentially you have before values are, with the naked eye, you can already say that they're kind of higher, and basically they decrease after watching that funny video clip. So basically we're being asked to calculate paired sample T statistics for these mood scores. Then we're using a one-tailed hypothesis test that the video clip improves mood at an alpha level of 5%. Identifying a critical value and make a decision regarding the null hypothesis. Using a two-tailed hypothesis test with an alpha level of 5%, identifying critical T values and making a decision. Good. So first, let's calculate first with what we're gonna start. So first we're calculating, we have before and after values. So that prompts us already to think of independent sample t-test. Now we first calculate the difference, which essentially is easily calculated as after minus before. Gets us now, we have, how many individuals do we have? So let's create a participant ID. So we do 1, 2, 3. So we have a total of 12 individuals. So, oh, Newton. Okay, so mean difference, we're calculating now an average of all entries we have at hand, of all differences notably. We get a decrease of 2.41. So with the naked eye already we can conclude that there was a decrease in the mood score, which indicates that people were in a better mood at the end of that video clip. If we're calculating now a standard deviation, so we know already how to do that. Important is, as always, that we utilize the right formula. For a standard deviation of a sample, it is the sum of squares divided by the degrees of freedom rather than the sample size, or alternatively, the use of the STAT function. If you are calculating it for a population, you would use the STDEF.P function, or you would divide it by the sample size. So keep in mind that this is a different formula from the STDEF.P function. Utilizing this standard deviation, we basically can take the standard error of the mean. We can take the standard deviation, we're dividing it by the square root of the sample size, which we know is 12. That gets us a standard error of the mean of 0.35. Once we have the standard error of the mean, we can now, and that's what I would do first, we calculate now. So we need a one-tailed and a two-tailed critical t-value. So, and this is now the distinction that's important. So we have a sample size of 12. 12 minus 1 is 11. We have two different values now. We have for a one-tailed analysis, we have a critical t of 1.8 because we're finding the one-tailed in the upper row. 5% is the second column. That's our 1.8. For two-tailed, the 5% critical t is at 2.20. And that indicates already the problem with the one-tailed t-test. To understand it conceptually, if you are shifting now your hypothesis just on one side, you're basically looking at a lower t-value because you're basically stacking the 2.5% only on one side. That directs your hypothesis. If you have a two-tailed hypothesis, you're basically using 2.5% on both tails. So 1.8 and 2.2. So one-tailed is 1.8. So that's critical t. And two-tailed is 2.2. So this being said, for a two-tailed hypothesis, let's start actually with the two-tailed hypothesis first. So example C. Let's start with calculating the 95% confidence interval. If we utilize the lower limit and the upper limit, we are calculating now with the lower limit, we're calculating the mean difference minus the standard error of the mean multiplied by 2.2. 2.2. And conversely, we're calculating the mean difference plus 2.2 multiplied by the standard error of the mean, which basically gets us to minus 1.63. What do we conclude? If the 95% confidence interval does not include 0, what's the logical extrapolation and interpretation of this? Exactly, we're rejecting the null hypothesis because our null hypothesis for a two-tailed test is H0, that mean before equals mean after. Whereas the HA is that mean before is not equal to mean after in either direction. So now, this being said, if it doesn't contain the 0, we're testing against the null hypothesis that there's no difference. That means that our t-statistic is calculated as the mean difference of minus 2.4 minus 0 divided by our standard error of the mean. So that's minus 6.75, which is quite a substantial t-score essentially, right? So this being said, we're rejecting our null hypothesis. So what next? So this is C. So we're rejecting this at an alpha level of 5%, at alpha 5%. So if we would utilize now a one-tailed hypothesis, What's our null hypothesis in a one-tailed hypothesis? We are testing if there's an improvement in mood. So the research question is, we think that this funny video clip will improve the mood, so it will lower it. So that's our alternative hypothesis. So the null hypothesis is M before is smaller or equal to M after, right? So it's a little complicated. That's a little complicated conceptually, but think of it. You basically have a decrease in your mood, in your mood score, which implies that they're in a better mood, which is kind of counterintuitive, to be honest. But yeah, so that's the definition. So that means that the mood score before would be slow. Sorry, I tripped over my own example. So the mood before would actually be, okay, it's late. Okay, mood before, mood after minus mood before. If it's lower, it's better. So basically that would mean it would need to be negative. So we are saying now it's greater equal than 0, right? Or greater equal than 0, yeah. So basically that would be an improvement. So it would get greater, which would be a decreased mood. So it's either an increase or it's the same. So if we're having now an alternative hypothesis, that would mean that M minus M after minus M before would be smaller than 0. That would be an improvement in the mood. So now what that means now for our interpretation is that our T, which is going to be the same, our critical T for the one-tailed hypothesis 1.8, or in our case now it's minus 1.8. So we know now that our T is exceeding also that critical T from a one-tailed hypothesis, which we kind of knew because it's even smaller. So since also this one-tailed hypothesis, so this is true for minus 1.8 when your hypothesis in critical T that is negative, so an improvement, which would be a lowering. So you're exceeding this critical negative 1.8. So that's the, so also here you reject at alpha 5%. So that would be the interpretation of a one-tailed test. So important is you can rephrase here your null hypothesis also for the two-tailed test as M before or M after minus M before equals 0. Essentially will be if you have a predefined anticipated change, this is the way you would need to phrase the null hypothesis in that regard, because then the difference that you're calculating has to be equal or greater than this anticipated change. So here the difference would be, for the two-tailed, it would be unequal to 0. So the one-tailed is a little bit trickier because you need to pay attention to the directions. But besides that, it's basically, it follows the same outline and the same approach that we've always done. Good. An interesting example was also this. So I just want to quickly also do this example. So we have here something that basically depicts two different exams, so an exam 1 and exam 2. So we are interested now in the differences from the first exam to the second exam. We're calculating our difference. And if we calculate exam 2 minus exam 1, that basically gets us to the differences. Then we can calculate it based on that. We can calculate the main difference, which is easily done. And we get from that also a standard deviation. And we can, based on the standard deviation, we can then quickly calculate. So we have here 8 students. So the SEM will basically be this divided by square root of 8. That gets us to the standard error of the mean. We can now calculate quickly a t-score, which is basically the mean difference minus 0 divided by the standard error of the mean, which is getting us to a t-score of 0.62. So now with a sample size of 8 and a degree of freedom, a corresponding degree of freedom of 7, we're basically looking at a critical t of 2.36. So 2.36 is larger than 0.62. So critical t is 2.36. The t is smaller. What this, so we are accepting the null, accept null hypothesis. So this is A. Example A and B. And why this? So we have now also an effect size to calculate, which is basically again this mean minus 0 divided by the standard deviation rather than the standard error of the mean. So we are basically having here an effect size of 0.22, which we know is a small effect size. So 0.2 to 0.5, 0.5 to 0.8, and greater than 0.8 are the categories as per Cohen's definitions. So we know that 0.2 and 0.5 is a small effect size. 0.22 qualifies as small effect size. So if we are now, and this is what example C, question C means to show. Now assume you collected exam scores from 1,000 students rather than 8. And the mean and the standard deviation were exactly the same as for the 8 students. If you were to use in a two-tailed test an alpha level of 5%, how would you basically test this hypothesis? So if you were to study 1,000 individuals, so the mean is the same, the standard deviation is the same, the standard error of the mean is now is now the standard deviation divided by square root of 1,000. So here the standard error of the mean is substantially smaller, which will essentially result now. So the critical t of such a sample size is obviously substantially smaller than the 2.36 we've seen before. And now we're back at our set statistics to Allison's point. So essentially we have now, in essence, again, a set statistic as our critical value, because 1.96 is identical with the set statistics. Because the sample size is so large, it basically will be methodologically be treated as a normal distribution from a population with the same critical values. So we have now a critical t was set in that manner for 1.96. So if we're calculating now our t, we're calculating our mean minus 0 divided by our standard error of the mean, we're basically by far exceeding that critical value. So if we had the same results from a population of 1,000 students, we would now reject the null. Notably, the effect size remains exactly the same and doesn't change at all. Has to, for logical reasons, because we're dividing still through the standard deviation. The standard deviation is the same. And that's why the effect size is so important, particularly when you have large sample sizes, because your hypothesis testing and whether you accept or reject the null hypothesis is substantially different than it was initially. But what remained the same is now the effect size. And that's why the effect size is so important, because it puts the emphasis on the difference rather than the sample size. All right, any questions to any of this? Any questions to the calculations? I think this is a nice way to show how important it actually is to pay attention to the effect size and how important that actually is when drawing inferences from your statistics. Any questions? Yes.
The exact effect size is the same, like in one case we expect the
Correct, yes. Because usually you do hypothesis testing based on the t-score, right? So you have a critical t-score. Once this is exceeded, you basically would reject the null hypothesis, which you do not do with a t-score that is smaller than your critical t. But if you have a very large sample size with the same variability, with the same standard deviation, you get a substantially smaller standard error of the mean. You remember the conversation we had. It's like the sample mean, the distribution of the sample means does not vary as much because you get a much more accurate estimate with larger sample size. So you get less variability with larger sample size. Therefore, your standardization of your differences is basically showing that there's a larger t-score than you actually would expect with a smaller sample size. And the effect size only puts the weight back on the difference rather than on the sample size.
So you wouldn't say that our results were important? You wouldn't like classify our results as being important because the effect size is the same.
So you would report it as such. So you say, based on our sample size, based on that sample at hand of 1,000 individuals, we're rejecting our null hypothesis, we're accepting the alternative hypothesis, and we draw the inference, or we would conclude that from exam 1 to exam 2, there was an increase, modest increase in score. However, the effect size was actually only very small. Oh, small, not very small. It was a small effect size as per Cohen's conventions. So the interpretation of that would be that yeah, you still you see a modest effect, but it's essentially in the greater realm of things, in the greater picture, it's a very small effect. So if you were, for example, if you were test in the medical field, you test an intervention, and you test the intervention in, like, let's say 1,000 patients, you would say, okay, so I see, because of the large sample size, I see an improvement in blood pressure, cholesterol, whatsoever, whatever you're testing. But clinically, it's not really relevant because the effect size is very modest and very small. So that's why the effect size is so important, because it helps you to make decision making on how relevant is that difference that I'm seeing, or is it just driven by your sample size? So that's why effect size is really very important metric to use. Make sense?
Yeah, thank you.
Yeah. Any other questions? If not, have a nice evening. See you on Zoom on Wednesday. Link is posted. Thank you. Brother. Thank you. Good night.